divided by x minus 4. Although some of you may believe this is going to give us a hyperbola, you see that x minus 4 in the denominator, not so fast. It appears as though it gives us a straight line. Well, appearances can be deceiving. So what we need to do is we go back into our calculator, go to our table, and take a look at the points that it gives us. And something should jump out at you right away. And that something should be at the value of 4. There is an error. Right here, there's an error. Okay, so that means we do have a straight line. However, at the value of 4, there is going to be an error. So there is an open circle there. And our curve looks something like this from that point. So I've been down through my checklist. First, does f of 4 exist? And again, if I go to my table, I can already tell because there is an error there, it does not exist. There is a hole in that graph. No, it is undefined. So do I need to go any further? In this particular case, I do not. The graph is not continuous. 5-82. Consider 3 conditions of continuity at a point as stated in the box above and sketch the following function. So we want to sketch a function that is discontinuous, where x equals a, satisfying condition 1, but not condition 2. So we want to, we would like to have a function there where the x value exists, but the limit does not. So we're looking at a piecewise function as our easiest option. Similar to part C in the previous problem, where we can have an actual coordinate that is part of the function and that does exist, but have a hole in the graph for the second piece, so that when we're calculating the limit or determining the limit, we trace our fingers and our fingers don't meet. So therefore condition 2, limit existing, is not true. Part B, a function that is discontinuous at A that satisfies condition 2 but not condition 1. So there we're looking at one where the actual point does not exist, however the limit does. So even the one we started the day with, that looks something like this. Could be an option. Alright, and finally a function that's discontinuous at A satisfies both conditions 1 and 2, but not condition 3. Let's see here. So we're looking for a function where the point exists and the limit exists. However, the two are not equal. And I guess that would be the one that I drew here. The point exists, the limit exists. However, the answer we get for the two of those does not. 5-83. We're going to look at a new graph here, sine of x divided by x. What is the domain of this function? So if we go to our calculators here, because that might be the best place to start, since we might not know what that looks like off the top of our heads. Type in sine of x divided by x. I'm going to go zoom trig, since this has a trig function in it. That will be the sine, for all of you that know what a trig function is. And it appears as though the domain is continuous. Not so fast. Let's go to our table. And in our table, something should jump out at us right away, and that is the fact that we have an error at 0, because x cannot be 0, because you cannot divide by 0. So what is the domain of this function? The domain of this function should be all real numbers not equal to 0. Everything else should work. Make sure your calculator is in radian mode and sketch the graph. Be sure to indicate its domain restriction on your sketch. So what you can't tell is that graph is kind of cycling about the x-axis. getting closer to the x-axis as it approaches infinity. Now consider the numerator and denominator as separate functions. Copy and complete the following. The limit of sine of x as x approaches 0. So if you think about what sine looks like, sine graph looks like this. So if I'm approaching 0 in a sine graph, from the left and from the right, my fingers meet, and the answer there is 0. Okay, what about the limit as x just approaches 0 of a linear function, y equals x? If I approach from the right, approach from the left, I'm approaching the same value again. Still approaching a value of 0. So the numerator and the denominator of f of x are both approaching what value? They're both approaching the value of 0 if I evaluate them separately. With the help of a graph or the table feature of your calculator, find the limit sine of x over x as x goes to 0. So if I'm using the graph, I can see as I come from the left and I come from the right, what y value am I approaching? I'm approaching the y value of 1. So the limit as x approaches 0 of sine x divided by x actually equals 1. So there's all sorts of conclusions that can be drawn here after doing part C. Some of you should be able to figure that out, why I end up with an answer of 1 in part D. Last, we have 5-83. What are the x-intercepts of this function? Sine of x over x. What happens as x goes to infinity? Find the limit of sine of x over x as x goes to infinity. Use a table if necessary. Does the graph of f of x equals sine of x over x have a horizontal asymptote? If so, what is its equation? And finally, write the limit statement as x approaches 0 for f of x equals sine of x. So, beginning here with what are the x-intercepts of this function? That's everywhere that f of x equals 0. So 0 equals sine of x over x. What values can I plug in there? Everywhere sine equals 0. So everywhere I'm going to end up with 0 divided by x is going to equal 0. Alright, so what x values am I talking about? Well, 0 is obviously out. X cannot equal 0 because we said that it is undefined at that particular place. However, where else is sine equal to 0? Sine equals 0 at pi. Where else is sine equal to 0? Sine is equal to 0 at 2 pi, 3 pi, 4 pi, yada, yada, yada. For all you Seinfeld fans. So the x-intercepts of this function are n pi, where n equals integer y, the pen's not writing, and n cannot equal 0. What happens to x? What happens as x goes to infinity? Well, again, if I would zoom out of this graph, it'd be something like this. Comes down, down, and it keeps getting closer and closer to 0. So does the graph of f of x equals sine of x have a horizontal asymptote? The answer actually there is yes. Why? Because all of you Algebra 2 fanatics would say as it keeps crossing 0, so it can't be an asymptote. Yeah, but what determines an asymptote is actually the end behavior of the graph. So because the limit as x goes to infinity of f of x equals a particular value, in this case 0, that means there is a horizontal asymptote as x equals 0. Finally, write the limit statement as x approaches 0. We already did that. That ends up equaling 1.